Hey folks, welcome back to Tomorrow Today. This is your host Andy, and I'm here with my co-host.
Me. It's Nash, guys. It's me.
It's Nash.
It is.
So today we're talking about some really exciting and uplifting things. You ready for it?
I'm ready for it.
Superbugs.
Oh, wait,
global catastrophe.
Oh, okay. So
like not just really big bugs or something, or like
yeah,
cool
no, I was
bugs,
thinking like
ripped
superhero
bugs.
bugs, and then you ruined it
like
right
Tickman.
away.
Do you remember Tickman?
No, was Tickman a thing?
Yeah. It was like a really weird thing. We're not going to talk about Tickman. Not today.
We can't get distracted.
That's another
Tickman.
one. Another day.
That's not a superbug. Okay, I understand now.
All right, so superbugs, the ones we're talking about are like antibiotic resistant stuff. So the shit that you're afraid of if you go to the hospital and catch.
Like a serious staph infection.
Yeah, like the stuff that they're like, hey, we tried these drugs. They're supposed to work, but they didn't. So...
Got it.
That kind of stuff. So this is one of those things I think I remember being a kid back in the 90s, and you'd see on like a Dateline 60 Minutes or something and be like, is this the thing that's going to end humanity? Like, up next, we talk with researchers on blah, blah, blah. And there's always this thing that was impending.
Global warming.
Like global warming, which means obviously it's never going to happen.
Right, we're safe.
Yeah, so global warming hasn't happened. They've been talking about it for 40 years, so clearly it's never going to happen.
I mean, it still snows, Andy. It still snows, so...
I mean, the trees are all budding out, and it's April here, early April. Yeah, that's a normal thing. So what I want to do is just kind of outline a little bit about what this conversation kind of involves.
Sure.
Because I think there's a lot to it that we don't really understand. So like I said, this is something I think most people have heard of, but it doesn't really mean anything. It's like, that's a thing that exists, and I know I should be worried about it, but it kind of is like out in space and like the news and not like in my hospital that I go to or whatever. So for context, the CDC reports that in the U.S., someone actually dies from a superbug every 15 minutes. And there's more than 2.8 million antibiotic-resistant infections occurring in the U.S. each year, which causes over 35,000 deaths a year.
Damn.
So yeah, it's like not as insignificant, I think, as we think because it's not in the news. Like it's killing people. It's killing a lot of people.
Jesus, yeah.
The challenge is that we've had... this idea that we could do whatever because the future is going to, like, we've basically treated the medical field like the stock market in the sense of like, oh, we've always had 10, 12% growth, so we always will. We'll say that there's no guarantee that we're going to continue, but everyone just kind of assumes like, you don't go to your retirement person and they'll be like, yeah, you're not going to get, you're only going to get 2% growth because there's only so much growth left. The years of that fast growing period are gone. Even if you know that the past isn't the future, we just kind of treat it that way anyway. So basically what happened was that during World War II, as researchers started realizing how to utilize penicillin to cure like battlefield infections, what we saw after the war was like this massive explosion in industrial production. And it was, the American way, like, if it's worth using, it's worth overusing.
Yay.
So they just used it for everything. And there wasn't any like really well understood regulations around making sure that it's used appropriately and like actually kills everything off. Alexander Fleming, the guy who actually was awarded a Nobel Prize in 1945 for some of his work with penicillin, actually stated at that time, like, there's a failure coming for this. We need to be prepared. And basically what he said was that if we use non-lethal amounts of penicillin, it's going to make shit that is resistant if you don't kill it all off. And it really only took like as much as it's like, oh, this is in the 1940s. It took only a couple years to start already seeing penicillin resistant strains of various stuff. All good things.
Just it's how you want it, really. I mean, you want the bad news right on the tail end of the good news, I think.
Yeah, it keeps you nice and level, even-keeled.
Tampers the hope.
Yeah. So, in classic market fashion, very quickly there were responses to this, and it was like, okay, we have all these pharmaceutical companies that started just pumping out alternatives to penicillin. And at first it was like, cool, like this is great. Then they had all these issues, which we're not going to talk about, of like, basically why the FDA had to start getting involved because they're making things that technically worked, but also caused like other really bad stuff.
Well, the free market provides, you know?
And it provided a lot of
Yeah.
debilitating health issues.
Perfect.
Yeah. Basically, what happened is then the FDA started getting involved. They started, as these low-hanging fruit that got produced very early on, either became no longer usable because of the fact that it was like causing major health issues, or because now the things that they had introduced as replacements for penicillin didn't work anymore. It started to become like pretty quickly like, oh, this is a real problem. And part of this is because pharmaceutical salesmen were pushing doctors to use it for everything. And part of it was that doctors used it and it worked in the short term. So they're like, okay, we'll just keep doing that. Like they're not researchers. They're just like your primary care physician. He knows what your heart's supposed to sound like, not like the chemical makeup of like various drugs.
Thanks for going to med school.
Why did you even go then?
Yeah, for real.
As much as it'd be nice to just be like, okay, this is primarily an American problem. By the 1950s, the World Health Organization was like, this is a huge issue. And then it just kind of fizzled out. And I would probably just blame that down to like...
Classic America.
Classic America. We usually have a say in that kind of stuff. With all this going on, basically shit got bad and we're like running. It's like the evolutionary arms race where we're just trying to stay a little bit ahead of these bacteria, but the writing is on the wall that we're kind of at the end of that we've exhausted all the different avenues for the materials that we have available for us today. There's only so many ways we can keep changing the things we already know. And that's kind of where we are right now, which is really exciting and happy.
Yeah.
Right?
Thank you for nothing, mold.
So while there are bacterias that are really part of this like whole superbug thing, which is not part of the interview, but I'll talk about it just a little bit because it is kind of interesting and kind of creepy and scary. The main bacteria that mostly people are talking about when we're talking about superbugs is Enterococcus, and it's kind of the godfather of superbugs. Now, back in the 80s, they were the first one when you heard about the superbugs that people were usually talking about.
Well, they were going to make you an offer you can't refuse.
The offer you couldn't refuse was dying.
Cool.
Yeah. So
Still can't, actually.
Yeah. Now, the thing that's interesting about this bacteria in particular is that evidence kind of suggests that this is actually something that came out of the oceans and onto land with, like, the stuff that came out of the oceans.
With me?
Not you personally.
Oh, like we walked out together, is what you're saying.
Metaphorically, yes.
Yeah, got it.
And it's actually basically existed inside, like, the intestines and stomach, or the intestines of basically everything that's lived on the land since land.
So this is a turf war.
It's a turf war in the sense that we fucked up and now they're asking us to pay the price.
Yeah, so like we should have just stayed in the ocean and not found out.
No, we came out. They were cool with us coming out.
Oh.
Like, and what's cool is like the bacteria then theoretically also like the bacteria that this is was also in like the stomachs of like a T-Rex and like the first snake that was like on the land, and that's just like kind of cool that we have this weird lineage and relationship with this thing. Even if it wants to kill us, we've got history. Like,
oh, but maybe that's why this is like one of those like long-standing family disputes that's like ended in murder every single generation.
Maybe the mass extinctions were all the friends we made along the way.
Maybe the asteroid was one of the friends we made along the way. Wow, wouldn't it be great if he visited us today, right now?
Right this minute.
Yes.
So Dr. Ayesha Khan, who I interview, you'll hear in a few minutes, actually focuses on a fungal disease called Candida auris, which, unlike almost all other fungi on the earth, can survive in the human body's high temperature. And the question is, why is this happening? And also, what are we going to do about the fact that it's a superbug fungi? Like, what is the solution and how have we ended up here? And a big part of this problem is climate change.
Awesome.
Yeah. So climate change has warmed up the earth. So the things that live on the earth also have to deal with, that selective pressure of heat and I wonder if things try to survive as the planet gets hotter, if they're better at surviving in our bodies. I don't know. What?
Than we are? Like,
No,
it's
like,
going to inhabit my body and, like, wander around?
I mean, it's a fungi. It's not SpongeBob SquarePants.
But that's kind of what my thought process was on that one.
No, this is Patrick.
Right? No, this is a fungus. They used to be Nash.
No, this is Patrick.
The lid. Patrick.
So yeah, we talk a bit about what the different pieces that kind of make up this unique clusterfuck puzzle that explains why we're at where we're at. And it's mostly unfortunate, and the solutions are simple but also very difficult.
Is it solve climate change?
And some other things, yeah.
And invent new medicine that basically...
And some other things, yeah.
Perfect. Just what you want.
Just a few things.
How is this one simple? You said it was simple and yet...
And yet.
Isn't simple at all.
Yes. Classic science fashion.
Yes.
But yeah, that's pretty much it. I think you guys will enjoy the interview. It's really interesting and not at all depressing. And for some reason, I only do very exciting and optimistic things. Tomorrow, today. Hopefully, we're not here for it.
Today?
Today.
Too late, motherfuckers.
Dr. Khan, thanks so much for joining us. Could you tell our audience a little bit about yourself?
Yeah, so I'm by training a infectious diseases scientist and a clinical microbiologist. So basically, I specialize in the diagnosis of infectious diseases and work with other clinicians like infectious diseases doctors to guide and to use diagnostics and use tools to basically guide treatment. And so I do both. I guess it's a little interesting for me because I'm both in the world of research, like molecular basic science research, where like I'm on the bench in the lab, but then also get to see the patient care aspect of it. So I can essentially bridge the bench to the bedside.
It's a good time, for better or worse, to be an infectious disease, I guess.
Yeah. I guess people have an odd amount of awareness about what I do now, and no one had any idea of what I did before 2020.
Yeah, your value on the market just went way up. We had talked a little bit before we'd started recording about some of your work, specifically around like bacteria and antibiotic resistance. So for folks, I think a lot of people have heard the term antibiotic resistance, and every once in a while it makes its way into the news as like this big like fear thing, and then it just kind of disappears. And I feel like I've been hearing this for like 10 or 15 years now, and it's like, okay, well, is this really a thing, or like what's going on? And, you know, as somebody that spends a lot of time researching it, could you like explain it in like layman's terms?
Yeah. So, I mean, I guess, everyone sort of has a grasp around evolution or has learned about evolution at some point in school. And I guess learned that evolution allowed us to go from single cells, like, and those used to be bacteria, to what are now maybe the most destructive, but definitely the most complex species on the planet. But evolution also is the same process that all microbes, so not just bacteria, but bacteria, viruses, fungi, and parasites, used to evolve to any sort of environmental danger or stress. So they just essentially have to change their genetic code to adapt to the environment. But it's really cool because trying to understand how they do that helps us understand how we evolve. And it's essentially studying like a contained ecosystem, right? Like a microcosm of life, and trying to understand like what are the strategies that they use to prevent themselves from dying, essentially. And the way that I do it is trying to understand what techniques, specific superbugs, like the most, I guess, fatal infections that you can get in the hospital that are resistant to all antibiotics. So you kind of run out of options and you have no more antibiotics that you can give a patient because the bacteria itself is resistant to all of them. Then taking that bacteria and taking it back to the lab and trying to understand how it's doing it. And it's kind of interesting because a lot of the times it's very intuitive. So for example, if the way that an antibiotic kills the bacteria is by going inside and taking apart like the cell wall, right? Like the protective layer that surrounds the cell to protect it, then the way that they become resistant is by basically changing the architecture of the actual cell wall. So the antibiotic can't recognize it anymore. And like, it's really intelligent, but it's a very like intuitive way of thinking. If that's how you would, you know, if there's a target that an antibiotic is coming from, then you just change the target to adapt. So it's kind of cool to try to like understand how, like, and these are single cells that are able to do this.
this is a terrible metaphor, but it like reminds me of like the like cheesy like monster movies, and you find out there's like this very basic thing
Mhm.
that actually will work against them, and you're like Independence Day. It's like, oh, they have this giant like spot in the middle that's just like this really obvious weak point.
It is. It is. I mean, and that's like, so one of the I guess the biggest paper, and I want to say it big in quotations, as in the highest impact or whatever paper that I had, that was a culmination of my PhD, was published in the Proceedings of the National Academy of the Sciences, and that one basically discovered a new mechanism of antibiotic resistance. So basically discovered that bacteria could do something that we didn't know they could do before, and it was to defend themselves against this like last resort antibiotic that we throw at them when we don't really have many options. And essentially what they do is send out this like sentinel protein called LIAX, which is like just the sentinel that just goes out into the environment and is constantly surveying the environment for danger. And whenever it finds an antibiotic in the environment, it basically just like screams back at the cell that there's something coming. So they have a heads up. They have like 12 minutes basically to get a head start and essentially change the architecture of the entire wall. So by the time the antibiotic actually arrives there, it doesn't recognize the cell anymore. And so it's like this, like just the idea of like, if you could send out a sentinel that could just be out there surveying, you know, the environment for danger and like prevent it from actually getting there, you know, by time, essentially. That's like a pretty simple concept I think we think of. But the fact that a single cell is
like
able
a backup
to do
camera.
exactly.
like the sensor ones.
Exactly. Yeah. You just have a tell that goes off to give you some time to like, you know, basically build up reinforcements and adapt to whatever like invaders on the way. So I think it's just interesting that a single cell has kind of figured out how to do that. And that's pretty much how they're able to adapt to just about anything, which is why I guess they're here for so long. And we're still dealing with, you know, drug resistant infections and infections of all kinds. And at the same time, I mean, we need bacteria to survive. And I think that's something that now people are more aware of, that we have good bacteria that we depend on to be healthy, like in our gut and in our entire body. Actually, there's more bacterial cells in a human body than our own cells, I guess. So now we're understanding that there is this like balance between existing, you know, in this intricate ecosystem where we need them. But then you also have, when things get thrown off in the environment, that's when you have like the bad ones take over, and then you have a pandemic essentially.
Yeah. Power vacuum.
Exactly.
Yeah. Nothing goes wrong with power vacuums. What's interesting about this, like I said, is that it seems like this is like this thing that we've been afraid of forever,
Mm-hmm.
that like we're going to have this super bug, and like not even talk about like COVID, but like,
Mm-hmm.
you know, an antibiotic resistant thing that is going to just like wipe out people.
Mm-hmm.
Like in terms of the work you're doing, is that like a realistic concern, or is it, as long as we keep working, we can stay one step ahead or almost one step ahead, and that's good enough?
Well, I think, yeah, but yes and no. So I think, yes, it's true in that it is going to be, we call it an evolutionary arms race because it is like an eternal, like, and that's, I think maybe the only thing that we can do is kind of live in the symbiosis with, you know, everything in our environment and sort of make sure that we're keeping the balance. But the problem is now we live in a society where that balance is being thrown off so often because we have like systems like capitalism that are essentially endlessly extracting and exploiting the earth at a rate where it can't possibly regenerate itself. And I think people sometimes that connection is lost, that how does like the whole political realm of our economy, for example, connect to the pandemic? But I think hopefully maybe it is a little bit more clear with COVID. But maybe people just understand that, okay, we never had the systems, for example, like healthcare to take care of people. So when you do have a pandemic, it is obviously going to be devastating because we never invested in public health. But also the whole reason that a virus like SARS-CoV-2 emerged in the first place is because we have such a drastic change in our environment right now, where you have, for example, deforestation, where forests are being cut down. And then you suddenly have all these animals that used to live in the forest that are now coming in close contact with people. And that directly contributes to what's called zoonosis, is like zoonotic events, which is when viruses jump hosts, essentially, because now they're being forced to adapt to their environment. And those are not really things that we even anticipate or should be dealing with, right? But are now having to deal with. Or, for example, rising temperatures. So when things get hotter, that increases the rate at which viruses mutate. So they're basically having more and more shots at being able to adapt to being just as bad as SARS-CoV-2 eventually was. it takes like a million tries to get to be that infective and be that contagious and cause this much damage, right? And it's true that, like, I guess if you look at before the 1980s, I would say 1980s and anything prior, the only emerging infectious disease, like anything new that popped up that sort of just wreaked havoc, was HIV/AIDS. That was, I think, historically what we think of. But then everything since then, you know, we've had Zika, we've had Ebola, we've had SARS, we've had H1N1, we've had swine, like we've had so many different things pop up in such like rapid succession in the last 3 decades, essentially. And that is not, that is at a rate that microbes are evolving that doesn't actually make sense to what they should be doing if they're actually living in a balanced ecosystem, but they're not. So they're under a lot of stress. So imagine just being under it. We're all living in a pressure cooker. And I guess the pandemic led to people feeling that, like what that actually feels like. And bacteria and viruses are dealing with the same thing. They're living in a pressure cooker, and they're having all of these crazy environmental changes happen that they're having to adapt to at such a fast rate, and they're able to do so. And that leads to and now we're going to see pandemics at a much more higher frequency. And this is just one. But we're just basically going to, now if you look at a map of like emerging infectious diseases, there's basically like 300 around the world going on right now. And that's besides, you know, SARS-CoV-2. So this is just a response to, I guess, a sort of a domino effect of capitalism ultimately.
Yeah. So I feel like there's a couple different pieces that we could unpack here around, and I just want to clarify a little bit for some of the points you made. So when you're talking about like the fact that zoonotic diseases, that these things that transfer from animals to people, I think a lot of people will be like, well, these animals have always existed and people have always existed around them. But you're pairing that with like the metaphor that I'm thinking of, and this might be wrong, is like when people immigrate to another place, their culture is evolving where they're from. So like take New Jersey Italians, they're my like favorite go-to. So like they left Italy in the 40s, 30s, 50s, around then, and the way their relationship to Italian culture is much different than an Italian person's, because that Italian person has existed and continued to evolve with that culture concurrently, while the New Jersey Italian is like a static,
exactly.
Like,
I mean, what you're describing is the ecosystem, like where some people have lived, and that is their home. So yes, indigenous people have coexisted in geographically isolated communities with like other animals, for example, in forests for a long time. Yes, but again, this is why I guess we think about decolonization as being so important to addressing the roots of so many problems, because indigenous communities focus so much on having this like value of land and connection to land and water and flora and fauna and maintaining the ecosystem balance. And essentially now you have like habitat destruction. So you're actually not just existing around these animals, you're taking away their homes, and then you're using all of the like whatever you took away to generate more as a means of production, to generate more and more and more, whether it's like fossil fuels or whatever it is, beyond what we need, right? So this is just excessive at this point. Yeah. And that basically that actually puts animals that would have never seen contact of like cities, like urban cities, are now in close contact and close proximity to not just humans, but environments that they would have never been in. So this is just like changes in temperature, changes in like humidity, changes in like everything that they interact with in their environment, like different minerals, different things that they have to process, like different metabolites. So they have to eat different, they have to drink different, they have to live different. And all of those changes, basically, it creates all of these opportunities for them to change in a way that could eventually be fatal.
Yeah, it creates a diversity of selection pressure.
Exactly, it is. Like, that's exactly what it's called, even in like the scientific term is selective pressure. It creates this like heavy selective pressure where they're just now mutating at insanely fast rates because they're being forced to find something that sticks. So to find like develop a trait to be able to like, for example, like one of the research that I did is trying to understand the impact of like increased rise in heavy metals in water, like mercury or lead or cadmium or arsenic in water, and what that does to bacteria. And they ultimately like become resistant to a lot of different antibiotics because they're getting practice essentially by becoming resistant to metals, and because they're having to, and they're going to do whatever they need to survive. So them finding a new host to propagate in is just sort of like, okay, this is just the next point in their evolution.
We've covered like the zoonotic component. We've talked about the selection pressure component. Now, I don't know if bacteria have like something similar to like how plants have like plasticity,
Yeah.
where they'll grow differently based on their conditions, and not necessarily in terms of selection, but literally how they form and shape.
Yeah.
Does that exist within bacteria as well?
Yeah,
It does.
yeah, it's and I think it's just interesting for me to study bacteria because you're studying like the oldest, most simplest life form. So you can then scale that up to being like you can only imagine then how human beings adapt, basically. And this is why I think it's interesting when people say that, they're like illnesses exist in a vacuum of their environment, because the way bacteria like do everything is they receive a stimuli from their environment, and then that stimuli literally shapes their response. So how they grow, how fast they grow, the shapes that they even have are like morphological changes they experience are directly related to everything and everything that they exist in. And again, some bacteria exist in nature, but a lot of the ones that exist in nature also exist in us. And sometimes, for example, if things in the environment will decide whether this bacteria stays a commensal, which is like the term that you use to describe a good bacteria, and we'll decide whether it's
something where mutual benefits.
Exactly, mutual benefits, and whether it switches to being a pathogenic like bacteria now, which is that something happened in the environment that actually caused that switch in that one cell to now become an infecting organism, when it previously would have just been something that just stayed there. So yeah, the environment basically, just like for everything, for plants, for us, it dictates ultimately how their traits are going to manifest.
I'm going to keep picking on this idea of like, because it just fascinates me, this idea of like superbugs with like super antibiotic resistance. Now, I think that the trend that most people think is that we basically kept using antibiotics to the point that they weren't working anymore. Now, is that a fair assessment, or is it more complicated than that?
It is one tiny piece of the puzzle. So it is true that, like I said, human beings have altered the ecosystem balance so considerably that it's led to a lot of these emerging superbugs. So one of them is overuse of antibiotics in clinical settings and in hospitals. And that actually is because and I don't know if people know this, but like all physicians, for example, are able to prescribe, and nurses and other healthcare providers are able to prescribe antibiotics. But there is a whole specialty called infectious diseases, because they're the only ones that are really trained on how and when to use them properly. So there is this gap where a lot of physicians sometimes don't prescribe the right antibiotics and in the right situations. So then you're basically selecting in the body of a patient, selecting for resistant organisms when you didn't need to even take those antibiotics. We're always talking about people taking antibiotics, for example, when they have a cold, right? So that's a good example. Or people not finishing their dose. But for example, that's not the only human intervention that's like causing the problem. Another example is like capitalist mass agriculture and factory farms, where one of the most common practices of scaling up production when it comes to meat production is to pump, chickens and cows and like poultry and like every animal that you can think of with antibiotics. So they end up being just you get more meat out of it. And at the end of the day, what this means is we're consuming, and this is really interesting because then we end up consuming that meat. And even though there might not be like live bacteria, for example, the genes that are actually giving them the quality of being resistant to an antibiotic can be in that meat and then be in our gut. And then this cool thing that bacteria can do is just pick up DNA from their environment and just like incorporate it. And
Jesus Christ.
Right. So this happens, this is why it's led to a lot of gut bacteria that now are super drug resistant and can cause infections. So there's a lot of human practices where we widely use a lot of antimicrobials. Like, for example, even the fact that a lot of times in hospitals, you use like chlorine and a lot of these disinfectants to like clean like a lot of surfaces, but a lot of times those are overused in different environments, and those are also selecting first. So there's a lot of like different points of human intervention that have led to this. But at the same time, there's this really interesting paper in Nature that was published a while back by a collaborator of ours, where he just sent a bunch of graduate students out into like near the polar ice caps in Canada, and they dug through the permafrost and then took these samples and took it back into the lab and essentially did what we call like molecular clock analysis, which is to try to understand like how old whatever you're finding is, how old the DNA that you're finding is, and discovered that you have the existence of genes that could code resistance to antibiotics that are way, way, way before humans ever existed. So basically, this is something that's so ancient, and that's because we get antibiotics from nature. And I think people know this with like the story of penicillin, right? You know, like we got penicillin because it was just something that a fungi happened to secrete in their environment to prevent themselves from being, you know, from being attacked by this bacteria. And then we isolated that compound and then created a drug out of it that could be put into patients. And a lot of the antibiotics that we get are natural compounds. And that's partially how we discover new antibiotics. So bacteria are constantly not just evolving to stressors, but they're constantly evolving to each other in their own ecosystems. So a lot of times these genes, or at least like predecessors of these genes, have existed even before we existed on this planet.
That's cool. I mean, it's a little frightening, but it's cool. You brought up the polar cap, so that's like a natural segue to talk about climate change and how, you know, I think most people understand that climate change is like accelerating things, like everything. But how particularly, or how explicitly, I guess, would you describe the relationship between like climate change and like infectious disease as an area of study, and like what you're seeing, how that plays into what we're talking about, this idea of the reality that we're in some ways we're in this race with biology or with bacteria to not die, basically.
Yeah, and I mean, we can start like in a very big scale, I guess. If we think about ourselves and just think about how we were taught to think about what makes up a human being. So we were taught that, okay, there's a bunch of individual cells, and when they come together and there's a bunch of cells, they can make an organ like a heart or a liver. And then when a bunch of organs come together, they make up an organ system. So then you have your like circulatory system or your nervous system. And then you need a bunch of those systems to come together to form a fully formed, you know, human being. But then that's not necessarily where that ecosystem ends. You have a bunch of people then that live together to form a community. You have a bunch of communities then that live in their ecosystem with like flora and fauna to create like ecological niche. And then you have Earth, and then you have a solar system, then you have a galaxy, and then you don't really like stop this idea of how things are connected. And it's interesting how we
like
think
the
that
nested systems.
Exactly. So the way that if you think about it in a human being, like it's impossible to isolate an infection that's in your kidney, for example. So you could have like an infection that starts in your kidney, but if you do nothing about it, it will spread everywhere and kill you. And that's just the arc of how things work, because everything's connected. But I think with the pandemic, people saw that that's how our whole planet works, because it is one organism, one giant organism. And if you can think about human beings as individual cells, that if you have an infection in one corner, it's going to spread and kill everybody at some point. But like imagining that in a little bit more complexity, it's if you have problems in one corner of the earth, they have already permeated and affected everybody in ways that we don't even understand, right? And this is then taking that analogy to understanding how systemic oppression affects everybody. And ultimately, not just infectious diseases, but any sort of disruption of ecosystem balance causes this like butterfly effect that is very difficult then to undo unless you sort of restore the ecosystem in the way they used to be. And that's essentially what capitalism's done. It's disrupted the ecosystem in such a significant way, where if you think about a big picture, we're extracting Earth's natural resources at a rate that is so fast that the Earth is not able to possibly regenerate at that rate. So
yeah, what's the Earth overshoot day? The day where we've used the amount of energy that's on. I think it's like August 8th or something like that.
Yeah, and I think so now. Like, and I mean, having read like all of the papers that led up to the estimate, I think it's pretty reasonable to say that the estimate is about like 7.2 years or something is how long we have to drastically change the arc of how we do everything, like how we extract from the Earth before mass extinctions just start happening, and we're headed for the trajectory. So, and I think if you think about one way that can happen, it is like infectious diseases, because the pandemic, I think, was a solid example and a warning to people of what's to come. Because again, that same idea of disrupting the ecosystem, and in this case, through deforestation, habitat destruction, urbanization, and accelerated like a fossil fuel production, and all of that contributed. And then you have on the other side, no public health infrastructure, no universal healthcare, no universal income, no universal housing, no universal food, water, nothing. So there's so much of the ecosystem that's just gone haywire. And then you have viruses that are trying to do their best to mutate and to adapt to the environment that is so drastically for them such a big stressor. Now they're having to survive in higher temperatures and next to hosts that they've never had to survive in before. And the only way they can do that is by accelerating their mutation rate. And that's literally why we see so many different new infectious diseases that are popping up around the world. Like I'm sure people heard when we heard of like Ebola for the first time or Zika for the first time, like those, we call it emerging infectious diseases because they never existed before, or things, and this is where antibiotic resistance is kind of scary because things that we used to be able to treat that were not a problem anymore will come back to be untreatable. And an example of that is, for example, anti-vaccine movements that in the United States that have led to measles outbreaks, where measles was effectively eradicated in the United States, and it no longer is because you have these isolated outbreaks that happen in pockets of the United States where you have communities with a lot of children that are unvaccinated. So this is when it's so many examples of like the outcome of a unbalanced ecosystem.
So like you're talking about like measles, and I'm going to ask maybe a stupid question, but so if people continue to allow these outbreaks to happen, it's possible and likely eventually the vaccine we have won't work anymore?
Yes. So basically it's similar to kind of what we're having with COVID right now, right? Like where I think the arc of maybe similar to what people understand with the flu. The reason we need to get a different shot, a flu shot every year is because the strains, specifically with influenza, evolve so quickly that the strains that were circulating and causing infections last year are not the same strains as this year. So you need the vaccine again. And if you then allow for the more infections that you allow, the more chances you allow for something to be contagious, to jump hosts, to infect other people, the more it's evolving. And it gives it more time to adapt, and more time to adapt means it gets way more different than the vaccine that you already have. And the further and further away it gets from that vaccine, you basically have what's happening now, where we're trying to develop booster shots to deal with Omicron, right? So, and we already do that with the flu. So this is why we actually have booster shots, because eventually you need to either remind your ecosystem or the thing has gotten way too different that we can't actually protect against the new thing that's coming.
Gotcha. Okay. So you've got all,
and I guess it's also, I'll also say it's also scary then for a lot, like with measles specifically and other eradicated infectious diseases, we rely really heavily on most people having been vaccinated to protect the many people who can't get vaccinated. So there's a lot of people that are immunocompromised, so they have compromised immune systems. So we can't give them vaccines because they will actually die. So they'll have adverse responses or adverse reactions to getting vaccines. So the way that we're protecting them is by making sure that a solid proportion of the population, usually something over 70%, are vaccinated. And now, because medical technology has advanced and we're having all these innovations, we actually have a larger immunocompromised population. So for example, cancer patients, and we have more people that have compromised immune systems. So there's more people that are unvaccinated and might not be able to get a booster, for example, until much later. So it's just increasing the risk all around when you break that herd immunity.
And then to my previous question on climate change, you're also now exposing these bacteria to more evolutionary pressure from temperature and also theoretically permafrost melt and what exists in that ice that is, like we were saying with my terrible New Jersey Italians metaphor, you're bringing these bacteria from a totally different time period and being like, hey, check out this new world, evolved differently than everything else because you're starting from someplace else.
Yeah, and there's a certain level of like unpredictability when it comes to that, because a lot of science is trying to stay ahead by trying to understand how things evolve and trying to understand and predict how things will behave in a different environment. But that's very difficult to do when you're dealing with something that you've never seen before. And bacteria, partly how they become resistant is not just one way they do that is by mutating and changing their genetic code so fast that introducing one mutation might be the advantageous mutation that gets them to survive in the presence of an antibiotic, and then that's selected for, and then everybody shares that mutation basically. But that's just one way. In other ways, for example, if there's two bacteria living next to each other and one's already resistant, they can also share genes and just give the gene that gives resistance to this other bacteria that is now resistant, that used to previously not be resistant. Or a lot of times they can even just pick up genes from their environment. So just open DNA that's not even from another bacteria. And this is what's, I think, really scary when it comes to like different environments, like permafrost melting, for example, that you might not have. I mean, you have bacteria everywhere, right? Like you have bacteria in like volcanic underwater thermal vents. You have bacteria living everywhere. But Even if you don't have live bacteria, you have DNA, and DNA lasts forever. So that DNA being picked up by bacteria that are alive and incorporating into their own genome, that's actually like a real, very real threat. And they already use that to evolve and adapt resistance.
So all I hear is that I should be very fearful for the future.
Yes, and also it has always been interesting to me that this evidence and everything I'm saying right now has been around for the last 30 years at the very least, to the level of robustness and reproducibility that it is to be able to give us all of these. And I think with climate change, we know that there's all of these alarm signs with people being like, we cannot go back very soon. Like it will be D-Day and we will be hurling towards extinction. And it is kind of crazy how with the pandemic, I thought that was a moment where there would be some sort of substantial shift, at least in us realizing you cannot create infrastructure from scratch. Like if you have a giant infectious disease that wipes through like the world, you're gonna need already to have universal healthcare and all these things in place to be able to respond adequately. And I thought people understood that, but then it's like things are quote unquote back to normal. And there is no change in public health infrastructure. There has been no reallocation of funding. There is no universal healthcare. The dumps have won and nothing has happened. So it is very interesting that it's almost like the universe, the environment in the ecosystem is giving you all of these different warning signs, being like, bruh. And this was a 2-year long, still ongoing warning sign. And I just can't wait till people just say before the 7.5 year mark, okay, maybe we can now do something.
Yeah, no, I think we'll go the opposite direction. And instead we'll just say, we've made it this long. Like, why? Clearly we can. It's just people will die.
Yeah. And that is the outcome of like what people, I think we saw that in the pandemic, right? It was actually maybe so blatant and so obvious to people, like the inherent ableism to capitalism,
yeah.
that your worth is measured not just based on your productivity and your like how good of a worker you are, but then only certain people are considered valuable under this economy. And then everybody's sort of discarded.
I'll ask you bluntly, where are we in like 20 years around this? Are we in deep shit, or are we like hopefully going to turn a corner, or like what not only where are we, but like what should we be doing, I guess, to address these very serious and existential issues?
I have both like some things that are hopeful and some things that are, I think, a little bit fatalistic, but that's fine. I think it looks a little like Mad Max. I think Mad like Max we're Light. Going to enter. Yeah, exactly. Light, exactly. With like severe resource shortages where we are entering like essentially where like water and air are going to be commodified, right? Because we're entering an era where everything is going to become just turned into a limited resource, essentially, even though it's not, but it's being controlled as such. But also pandemics are just going to sort of become the norm. And I think people are realizing that maybe you just have to live like this. And they're going to start popping up at such a high frequency where we're not going to be able to distinguish when we're out of one. And I think that's sort of the norm that we're going to have to get used to. But then also, I think what's hopeful for me is I felt very alone doing this work for like the last maybe 11 years because they're really like the world of science and medicine and the world of like political organizing was so spread apart and like no one talks to each other. But so when I was trying to bridge like science with social justice and geopolitics, it just felt like, oh God, why isn't anyone getting it? But I think in the next 20 years, what we're going to see is a merging of those two worlds. And like people in political movements having to increasingly like begin to rely on everyone from like scientists and doctors to be able to like support movements, but also like use research-based approaches to like solve our problems. And then also everything from like computer engineers and computer scientists to be able to like build, for example, like decentralized, infrastructure for us to be able to communicate with each other independent of state surveillance and things like that. So I think that world of like the separation between science and politics is just going to get really murky and we're just going to have to eventually just come together.
Cool. I guess not all bad.
No, I'm excited for that part.
Yeah, there'll be some good parts between the pandemics and whatever else might be going on. For folks that enjoyed listening to you talk, what would you like to plug for your various projects? I know you're really active.
Yeah, well, I guess all my work focuses on kind of what we talked about, bridging the worlds of science and medicine with geopolitics and abolition and anarchy. So the main thing, I guess, if you want to kind of have me break this down a little bit more, I kind of that's sort of what I do. I break down complex concepts in accessible ways for everybody. Is my Substack newsletter called Cosmic Anarchy, which is wokescientist.substack.com, and then that's also my Instagram, which is woke scientist, where I just give like little abbreviated versions of that.
Awesome. And you have a podcast coming up, right?
I do. Yeah, we have a podcast called Disorderland coming out.
Disorderland?
Which is actually, it is. It's called Disorderland. This is the first time we're talking about it. But yeah, it is. It's actually focused on abolition and psychiatry and psychology, and talking about how capitalist psychiatry and psychology are hurting us, and how we can turn to alternative models of care that are more community-centered. So yeah, keep an eye out for that. And also something that I'm doing more now is also just like working with people, I guess, one-on-one, and doing workshops and stuff to try to like talk about this more and just start bridging these things together already, so we can just skip to the next thing.
Awesome. Ayesha, this has been fantastic. Thank you so much.
Thank you so much.